Hey there. My name is Alex Golek, and I'm an engineering manager. I was previously at Reddit, but I'll be joining Patreon in November. And after the success of my last video on systems design, interviewing.io invited me to do another one, this time on algorithmic interviews. So, like last time, I'm going to be watching a recorded mock interview conducted on interviewing.io, and I'll be adding my perspective on what candidates are doing right, what goes through the minds of an interviewer, and what lessons you can take away from these things. And as always, I should say, I've spent many years interviewing candidates at major tech companies, but everything I'm about to say is being said in my personal capacity. I don't represent Google, Reddit, Patreon, or any other past or future employer of mine. So let's get into it.
Well,
Hey, how's it going?
hey, going pretty good. And yourself?
Pretty good. This is my first one of these, so pretty excited.
Okay, well then let's just dive on right in.
Yeah.
I think I'm going to ask you an algorithmic question, if that's all right.
Sure.
So there's a little selector box on the top right of the decoder pad. It says plain text now,
Yeah.
and you can pick any language that you think makes sense for an algorithmic type question, whatever you're comfortable with.
I'll probably do Python.
Python, okay, those are usually pretty good for these things. Okay, so we're going to start with a basic problem, and we're going to kind of add to it. So the first one is pretty simple, and the idea is you're going to define a function that takes in two strings and returns whether they are equal with respect to in a case insensitive way. So of course Python actually does have this, but we're gonna work through a couple additions to this once we get the basic one down.
Okay. Cool. I mean, there are other Python built-ins that could make this pretty easy as well, like turning the string to lowercase or uppercase, and then comparing it.
So you can use any of those.
Okay.
And then we'll talk about the implications of using those and all that kind of stuff.
So right off the bat, this is actually a very interesting question because can I use standard library functions? To give you some insight into that, as an interviewer, I don't actually know what language you're going to choose. So in Python, this is actually a very straightforward thing to do because in Python, as you're about to see, they have like just upper and lower functions that converts a string to upper and lowercase. If you were using like C++, that'd be a very different challenge. Different interviewers take a different philosophy on whether to allow people to use standard library functions. I find that for most cases, it's actually okay to let people use them because, as you're about to see, solving the problem is actually the easy part. A lot of times people fall into this trap where they look at an interview problem and they think, oh, this is like an easy problem. The standard library already provides this functionality. Why are you even asking me this question? But like really interesting performance and correctness implications fall out of that. And it's actually not a good idea, in my opinion, to just be like, oh yeah, this problem's easy. I'm gonna like be gung-ho about it. That doesn't mean you shouldn't use standard library functions. If your interviewer encourages you to or allows you to, you should because they're very powerful. But again, as we're about to see, you need to be careful about the implications of using them.
Okay, so that would look something like this. And I think that would do it. I'm assuming by case insensitive you just mean like basically letters of the alphabet.
Yeah. Mm-hmm. Okay. So let's just for fun write the in the shell.
Sure.
Case insensitive compare of ABC and capital ABC. See if that.
Yeah. Okay. Oops. Oh shoot.
Okay.
So this is an interesting point, and if you missed it, I want to underscore how important this is. The interviewer just encouraged the candidate to write a test case. That's a big deal. You should be writing test cases. If you're not writing tests in your own code, if you're not writing tests in your personal code, you're doing something wrong. If you're not writing tests in your professional code, you're definitely doing something wrong. Writing tests in an interview is also a good idea because it allows you to sniff out obvious errors, such as, like syntax errors, like little logic errors here and there. But it also allows you to solve the hardest of all questions that you may have for an interviewer, which is, does this look right to you? You don't have to ask the interviewer, does this solution look right to you, if you write a bunch of test cases and convince yourself that it looks right to you. So if you lead with a test case, or ideally multiple test cases, it really looks good because it shows you're fastidious and you're experienced enough to know that things could go wrong and you need to defend yourself against that. Also, I should add, all this is contingent on you having an execution environment. Many companies offer you execution environments. For instance, here they're doing Python. They have a Python REPL that the candidate can use. Google famously does not. Some companies don't. But in general, if you have the opportunity to use one of these environments, use it to your full advantage, because it'll really make you look good if you just write some code, test it, drop it on the interviewer's desk, and be like, okay, cool, what do you think?
Excellent. So what is the time and space complexity of this algorithm as you have implemented it?
I don't know how upper exactly works under the hood, but I'm guessing what it does is it likely builds a new string character by character.
That's an interesting point. I don't know how this function works under the hood, but I'm gonna use it anyway. I mean, that's not the worst thing you can do, but it really helps to know the properties and characteristics of the methods that you're using.
That would suggest that you have a linear running time, and memory is also linear.
Okay. As far as I know, strings in Python are immutable. So if you call something like upper, then it's going to have to return a new string.
Yeah, exactly.
Okay. So, and that's the best case, worst case, average case, always case?
Memory is going to be always case. I think running time would also be always case unless there's something I'm missing.
Okay. That makes sense.
So this is a good example of a runtime analysis, and you can see the interviewer is jumping in right off the bat with runtime analysis. Runtime analysis is something I expect candidates to volunteer. I'm not gonna, issue a no hire recommendation if you don't, but you really look good if you say, here is a solution I've written, here is its characteristics in runtime and space complexity. Highly recommend volunteering that information. In this case, the interviewer is very eager to get that, because that's kind of the argument for not using this to upper method. But I highly recommend being forthright about it.
So let's say that these are very long strings, and we don't expect this to happen very often. Is there an optimization we can make to this so that in the best case, it doesn't take full event time?
Sure. So not expecting it to happen very often, you mean that
that they're equal. So we're expecting that most of the time are not actually going to be equal.
Mostly they're not equal. Oh, okay. Interesting. So we could do something like, okay, I'll talk about it first. So we can go. Well, first you'll want to check the lengths of both of them.
Minor point: you might not actually have access to the length of the strings. For instance, if you have like very large strings that are so big that you have to put them on a hard disk, you might not have access to the metadata. That is splitting hairs, but FYI, keep that in mind.
And see that the links are the same. And if not, you can loop through both of them simultaneously, and do a comparison character by character, and compare them that way.
Okay. So let's.
Yeah.
Yeah. Sounds good.
So. And actually, I guess we don't really need this. Yeah. Actually, wait. Trying to find the cleanest way to do this.
Okay.
Oh, wait. Wouldn't want to create a new one.
Right, create a new what?
Wouldn't want to create a new. I guess this might terminate early, so this might end up being. Okay, let's do it this way. This way for now.
Okay.
And just to make sure that. Okay, interesting. Oh, right, of course.
Remember, tests help you avoid situations like this, and it's very good that he caught it.
I think we should probably have one not one failing case too. So like ABC with DEF or something.
Yeah.
To make sure. Okay. Excellent. Quick question here. I don't know if this is kind of an extra credit, but as you've written it, these are, I guess it depends on which Python we're using. These are Unicode strings or 8-bit strings.
Okay, so the interviewer is about to lead a conversation about Unicode versus 8-bit and encoding. Let's listen to it, and I'll give you my opinions on that afterwards.
But if this is Python 2,
which it is.
Which is, do we know? You guess?
I think it's somewhere. Python.
Oh yeah, Python 2.7.
Yep.
Can we think of any possible thing that might go wrong with this?
Yeah, I mean, we could compare, you could be comparing Unicode versus 8-bit strings here. And I imagine that might cause problems.
Well, let's even just think in terms of just both 8-bit strings, for example.
Okay. So ways in which this algorithm
have to fix this problem because the 8-bit string thing is kind of a mess.
Yeah.
So I'm just curious how familiar you are with what, like, if this was like, if I can, like if it was ABC and oops, that's not the one I wanted. ABC.
Yeah.
So let's even see if that works.
Yeah, curious.
So it doesn't.
It doesn't.
Which is okay. Can you think about why this isn't working?
So I don't know how the upper conversion happens behind the scenes, but I'm guessing it either ignores. Actually, one thing I'm curious about is what that actually is for these strings. Right. So it doesn't get converted. So it probably has some whitelist of characters that it only works on.
So interestingly, what you'll notice is that Python is pretty good about this if you're dealing with. Oh no, it doesn't even work. Huh, that's interesting.
So if we did
I would have guessed that would have actually worked, but
oh really? Maybe in Python 3 that works. Yeah. But let's see what happens here. Oh.
Wow. Huh. Oh well. In any event, that's funny. I actually would have thought that calling the Unicode strings would have fixed your problem, but not. In any event, let's not worry about that case for now. That was just kind of an extra credit one.
Yeah.
So here's my thoughts on Unicode in this context, and I'll try to generalize it, so you can take bigger lessons to it. One of the purposes of a algorithmic interview is to evaluate you on your algorithmic knowledge. And that means designing, applying, modifying, and really just understanding algorithms. And a topic such as Unicode falls outside of that, in my view. I prefer, when I design interview questions, to try and strip out as much complexity as possible and to sweep out as much unnecessary complexity under the rug. So this is actually a very interesting and worthwhile topic to go into, which is, what does uppercase mean in Unicode? Because not every language, not every script has an uppercase mode. The implementations are janky because you can see that this A with an accent, you would think that would become an uppercase A with an accent, but it doesn't for some reason. The APIs that are provided by various languages are esoteric and complex. In my view, this was a distraction. If I were an interviewer, I would try not to get into this situation because one, it's just a waste of time in my opinion, but also there's a psychological effect. If you take a person who's under pressure, and we have to be honest here, interviews are high pressure environments. If you take someone who's under pressure and ask them questions that they don't know the answer to, they're gonna feel uncomfortable. And if someone feels uncomfortable, they're more likely to get stressed and not perform at their best. So as an interviewer, I would just say let's assume that we're just dealing with the standard 26 characters of English. I disagree with what this interviewer did here.
But okay, so that's all good. Now, what is the best and worst case runtime and space complexity of this one?
Well, best case is that the first character is different, so that would be O of 1. Worst case is still O of n. So average cases, but depends on what your input looks like. But yeah, memory is memory is the same as that. Yeah. Because it's also memory is best O of 1 and at worst O of n.
Is it O of n at the worst case?
I believe so, because you'd have to create a new copy of each character because I'm using upper here.
But is it going to keep those characters around? Like, do you need all n of those?
That's a great point. No, it's not going to use those over and over again. Or sorry, yeah, it's not going to create new ones each time and keep all of them around. So yeah, I believe it would be of one then.
Of one, okay.
Yeah, this is a very interesting bit of ambiguity. So the question is, so first off, the candidate nailed it on time complexity. The question is, though, well, what's the memory or space complexity of this question, or of this solution? And what happened is there was a little bit of confusion here because the candidate thought it's a linear time space complexity because we are generating a linear number of objects. And that's actually a very reasonable thing to think, right? Like the challenge with languages like Python that are garbage collected is that it's ambiguous what it means, what we mean when we say storage or memory. Because if you create an object, as a refresher, if you create an object in a language like Python or Java or any other garbage collected language, that object is going to be used by your computation, and then it's just going to sit there. Like even after your function returns, even after there are no variables that point to it, it's not going to go away immediately. And this is in contrast to manually managed languages like C++, in which you as the developer are responsible for allocating and freeing memory as needed. So this question of like, well, how do you count those objects that are created after they're no longer needed? And the candidate is right here. You actually do generate a linear number of objects. So for the purposes of interviews, the space complexity takes a somewhat arbitrary or janky definition. Well, the way that I like to explain it is it's the amount of state that is necessary to run the algorithm. Or put another way, if after every single statement in your algorithm, the garbage collector ran and any variables or any memory that was not being used was freed immediately, how large would that residence set be? Now, the reason this is a janky definition is because, first off, the garbage collector doesn't run every line you run. And second, there are actual real-world engineering implications of having one implementation over another with respect to how they interact with the garbage collector. I can't imagine any interviewer caring about that at this level. Like maybe during like extra credit stages at the end of an interview, or like maybe at like super high level like embedded systems designers. I mean, you probably wouldn't be using a garbage collected language in embedded systems. Like you see, like I'm struggling to come up with an example in which that would be a relevant definition. So in general, ask yourself, imagine the garbage collector runs after every single line. How much memory will your program or your implementation need?
Excellent. So already we're improving on it. That's good.
And I should add, the difference here is actually palpable because in this example, if you count the objects that are hanging out, then you're talking linear, like the candidate said. But if you don't, in other words, if after every line the garbage collector ran and those objects disappeared after they were quote unquote no longer needed, then you have a constant runtime, a constant space complexity.
Now we're going to introduce a bit of a wrinkle, and that is, what if I want these to return true if they're the same, or their edit distance is 1 or less? So are you familiar with edit distance?
I am, yeah.
Okay, good.
Okay, so for those of you who are not familiar with edit distance is a value that is assigned to a pair of strings. So if I give you one string and another string, how many transformations, and I'll tell you what that means in a minute, how many transformations does it take to transform one string into the first string into the second? And transformations are replacements. So characters can get, if you're sort of scanning through the input string in order to create the output string, you have this imaginary cursor, and you can either replace a string, you can replace a character under your cursor. You can insert, which is you can insert a character before the character that you're looking at, or you can delete, which is you can take the character you're looking at and just throw it out and shift the whole string down. So replacements, insertions, deletions. Different versions of edit distance exist. For instance, certain versions of edit distance allow for swaps. It sounds like these two are on the same page, so they're probably thinking of a standard definition. But if you're not familiar with edit distance, we're going to be going into detail during this video.
So in that case, for example, like we've shown here, like this is going to be true, and this is going to be false, and this is now actually going to be true.
Mm-hmm.
I guess we don't really need that kind.
So we want right.
So in the case that I wrote, there was an insertion of a D.
Mm-hmm. Yep.
And you could also imagine that that a deletion would also.
Correct. Yeah. Yeah. Let me think about that.
And there's definitely a number of ways of doing this. So whichever way you want to think about starting it is totally
sure.
fine.
Yeah.
Long pauses to think are actually totally acceptable, just FYI.
So I'm thinking about whether I can still use this kind of like iterate through each string, but I'm wondering if that's constraining my thinking.
Mm-hmm.
Yeah, that's a wonderful thing to say, by the way. That's a very good sign to hear as an interviewer. I'm wondering if this has constrained my thinking. Because there are problems that seem very similar to one another. For instance, how do you tell that if the strings are identical or similar up to capitalization versus they're one edit away from one another? And that might feel like it's kind of, the approach that you use for the first one can be used for the second one. And for all you know, it can be. And not for nothing, oftentimes in these interviews, it is, especially these interviews that start with a simple problem and kind of get progressively harder, oftentimes the approaches that you take to the earlier problem can be applied to the next one, but not always. And it is contingent on you, the candidate, to know when you need to change gears and try something new and kind of come at a problem with a fresh perspective.
So basically what we can tolerate is one insertion or one deletion or one modified character.
I mean, we can define that any way we want. And I think actually it makes things a little bit more straightforward if let's just say insertions and deletions.
Oh, I see. Okay.
Just to get started.
Oh, okay. All right. Interesting. Okay. So then there's there's an algorithmic approach then where you that would just be a simple modification of well, maybe not as simple, but basically a modification of this algorithm where you keep track of both iterators and you iterate them together and if one of them is off, or if one of them has a mismatch, basically, you iterate the next one to see if it is an insertion or a deletion, basically. And actually, the action you would take would be different if it is truly an insertion or a deletion. So let me think about that a second. But
yeah, this is the core of the problem. And here's where things get hairy with this problem, because in the first problem, where all you want to do is a case insensitive compare, the moment you find two characters that line up but aren't case insensitive equal, you're like, okay, cool, boom, I'm done. And in particular, there is only one operation you can perform at that step. You say they don't match, the strings are not case insensitive equal, goodbye, we're done here. However, now there is an ambiguity. There are two things you can do. You can say, well, okay, let's assume I still have one edit to make. I can either resolve this conflict using a insertion or deletion, or I can use it using a replacement. And the candidate is kind of trying to figure out, like, okay, well, we have now branching paths. Which paths do we take? And we're probably going to have to try both of them. So watch how he approaches this problem.
The approach I'm thinking of involves still using that approach, the two iterators.
Okay.
So, and if you had, let's see, you could, okay, so I'm thinking now that I might use this method I've written as a subroutine.
Okay.
So the actual so that this might be then this would call basically this new install compare would basically call out to the case insensitive compare. And okay, so haven't fully thought this out yet, but let's see what happens. So if the lengths are not equal, then we check if they're within they're within one of each other, I guess. At this point, we at this point, we hypothesize that the longer one has an insertion relative to the shorter one.
Okay.
Yeah. Okay. So, I just realized that this problem is symmetric in that way. Okay. Then for actually, maybe we don't need to. I see. This will end up being a modification of the first method. So let's see. Oops.
So I'm confident someone out there in the YouTube audience is tempted to be like, actually, Python has some facility for this situation where I need to iterate over two items. Fair, I know, that's fine. But unless the code is absolutely unreadable, the aim of an algorithmic interview is to assess your algorithmic skills. So if the runtime and space complexity are acceptable, okay, maybe the code's not as idiomatic as it could be, but you know, it works and it's optimal.
Yeah, I see what's
Maybe, yeah, I'm just sorry, I'm working out like the fence post issue I have here. Oh, I see. Okay. I see. Let's see. We at this point we push the longer one more. So yeah. If those two aren't equal, or rather, actually, yeah, okay.
I could see a case here where I guess if you've already checked that the two are only one apart. I'm trying to think.
Whoops.
I guess there's no way to. I was thinking with this loop, the longer one could just have have twice as many characters as the first one. But you've already checked that the length.
They're off by one.
Right.
I'm not sure if I'm done or not. I think there's like something I'm missing that I need to see the case to.
Right. Well,
there it is. Okay, there's that phrase that you will find yourself saying again and again, both in your actual code, but also during your interviews. I'm not sure if I'm done. I can't tell if I'm done. You are the one who's responsible for knowing whether you're done. So how do you know when you're done? Reading through your code after you've written it is very important. You can read through it. You want to make sure that there's no syntax errors. But if you have access to an execution environment, you're not going to get much better than writing test cases and seeing what happens. So if you're not writing tests as part of your code already, you really need to get in the habit of doing it. Because in production, honestly, in real life, unless you work for a really janky company, you really shouldn't be submitting code that's not tested properly. Also, if you're in an interview room, there's no better way to show an interviewer that you have a professional mindset than to, first off, be in the habit of using tests, but also after you write some code, to take a step back and ask yourself, what inputs can I give to this code that will either break and expose a bug, or be correct and yield a correct output and convince me further that I'm doing the right thing. So I highly recommend adding test cases, provided you have access to an execution environment. If you don't, it's harder because you have to like go through the thing and step through. But even then, writing test cases allows you to focus your thinking and ask yourself, well, what special cases should I look out for? What edge cases? What off by one errors? What weird conditions could I have in this code that I'm not yet seeing? And test cases are a good way of stepping outside of yourself.
I mean, so first of all, like if the lengths are equal,
yeah. Okay.
I think there might be something else going on here.
Yep. Yeah, you're right. So let's see.
So right off the bat, right? If the lengths are equal, that's not a test case that this candidate considered.
If okay, I'll be lazy.
I mean, that's just the else statement of the previous one, right?
Right. Yeah, that's right. Oops, sorry.
That makes sense. I think if I want to return that.
Yep, I would.
Mm-hmm. What about the else of the previous if statement, the one on 15?
Right.
So this would have been caught if the candidate had a test case where the strings are different in length by more than one.
Then then they would just be
Yeah. Okay. Looking good. Okay. Well, let's run it. This part here,
sure.
it makes me like a tiny bit uncomfortable because it doesn't. It seems like you could do this multiple times, but I think actually because you're doing the check up here, then it's stopping it from actually being able to go multiple times. But
what do you mean by the whole thing could run multiple times?
Yeah, like this whole for loop could go multiple times where like this doesn't equal that, so then you push this one, you increment that one.
Yes,
and then
I see.
Going. But I think actually because of the way you've written this check up at line 15, you can't do it any more than once. And as you noticed, there's that symmetry to it.
Yeah.
This would hit either an insert or a delete by checking out the shorter one. So yeah, let's see if this works. I think it should.
Yeah, I'm not sure either.
All right.
Works on these cases.
Can you try that? Yeah, on those two as well. Look at that. Okay, very good, very good.
That's pretty cool. Yeah.
And then what's the runtime complexity and space of all of this? Okay.
So in the case where the strings are equal, it's the same as before. If in the case where they're not equal by one, or if they're in the case where they're not equal by one, runtime would look like it would also be between O of 1 and O of n. And in the case where I guess memory is the same as before too. Memory would be O of 1.
Yep.
For
Okay.
the same reasons.
Excellent. And now the really tough one.
Oh,
so
dear.
this is great. It's all correct so far. And now I want to add a parameter that says, instead of it just being hard-coded to 1, what if I put a parameter at the end here for how many
edit distance, or how many
distance I'm willing to
tolerate.
So if I did like 2 here, then that would still be true.
Okay.
Yeah, the last one, there's 2 deletes instead of just the one.
Yeah, now is when things get really real, because whereas before, so the first version of this problem is we allow ourselves 0 edits. They have to all either be case insensitive matched or the string's bogus. Then we allow ourselves 1 edit, and you can see how much more complicated this solution gets, because the candidate has to reason like, well, okay, we've got this 1 edit. Is it an insertion? Is it a deletion? We can do something with the lengths. But now there's an arbitrary number of edits. You can have 12 edits. And at that point, there's this exponential number of combinations of like insert, insert, delete, replace, 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 insert. Like there's every single edit that you're allowed to make can be filled with some number of edits. And therefore, you have this huge tree of actions that you need to perform, and you literally cannot keep that in your mind as you're reasoning through the algorithm. So if you remember early on, the candidate was like, well, is this approach even worthwhile? Like, do I need to change my thinking? Now is when that question starts to come back into play. Because if you do not fundamentally rethink the way that you're approaching the problem, you know, if you've gotten this far and you don't fundamentally rethink the way you're approaching this problem, you're not going to get very far. So these two are about to go on a algorithmic discussion, which might not make sense to you if you're not familiar with the algorithm that they're talking about. And I'm going to give you a breakdown of it in a minute. But until then, enjoy the run up to that conversation and just like look how hard it is to go from this solution to what the interviewer is asking for.
Okay. Yeah, I mean this is pretty hard because you could also have what shows the case more clearly?
Yeah, so one could be a delete and the other one could be an insert. So
yeah, exactly. Yeah. So yeah.
Yeah, exactly. So you were able to take a nice little shortcut by checking the length up here, because you took advantage of the fact that with only 1 edit, then the lengths are telling you something. Whereas here, the lengths aren't telling you quite as much because, you know, like you've shown in this last one, they could be the same length, but depending on what that number is, it's either acceptable or not acceptable.
Right. So still thinking about, I think I'll have to change my approach a little bit. Okay. So
sorry if you can hear my dog barking in the background.
Oh, no worries.
Dude, just mute yourself.
So unfortunately, I actually have to head out in about 5 minutes. So maybe what I can do is talk about what I would do.
Okay.
And a few approaches.
Yeah.
So this is worth talking about. Obviously, this interview is like 35 minutes in, and the candidate already has to run. There's been some miscommunication. They thought the mentorship session was 30 minutes instead of an hour. That's ideally, you'd want to avoid that in a real interview, but you know, things happen. However, if you run out of time, this is the thing you want to do. If you find yourself unable to solve the problem in a short amount of time, then you want to at least give a verbal description of what you would like to do. Because interviews, especially algorithmic interviews, they're about assessing 2 things. They're about assessing your ability to generate algorithmic ideas and your ability to code. Ideally, you would generate the optimal algorithmic idea and code the optimal algorithmic idea. But sometimes that doesn't always come together. For instance, in this case, time ran out. So I would give this candidate like a 95 on coding. It's pretty clear they can articulate their thoughts. Their algorithmic design, I would give them like a 60. They're not quite at 100% yet, but they're about to give an explanation that will illustrate what their algorithmic thinking is, and that'll bump them up to, maybe something like a 70%. And if you're stressed about, do I need to implement the optimal solution? Different people take different approaches. My belief is no. My belief is if you demonstrate that you're able to code, and if you demonstrate that you're able to design an efficient algorithm, like, I don't really need to see you implement the algorithm that you designed. Obviously, it works into your favor if you do. You kind of want to have that, but things happen, and it's not the end of the world if you demonstrate those two capabilities separately.
Yeah, sorry about that. Didn't realize it would go for this long, but this is fun. No problem. So what I'm thinking is, well, one kind of cheapo way is to actually implement the Levenshtein distance and kind of compare it that way. That would...
Okay. Now we have to start talking about Levenshtein distance. So I'm going to switch to my iPad real quick, and I'm going to tell you all about the Levenshtein distance. All right, so let's talk about the Levenshtein distance. The Levenshtein distance is a measure of how distant two strings are, and in particular, how many edits are required to transform one string into another. So you can imagine you're kind of sliding this cursor along from the left to the right of a string, and at each position, you're allowed to make either a replacement, an insertion, or a deletion. And however, or you could just do nothing and slide it along. The number of edits that are required to go from one string to another, or rather the smallest number of such edits, is called the Levenshtein distance. So I'm going to give you an example on this grid here. So suppose you want to take the word coping and transform it into the word coding. Now, you and I, as like human beings, can look at this and immediately be like, oh, we should just take that P and turn it into a D. But remember, we're dealing with this like abstraction where we're going to start with a cursor and we're going to iterate our way through and perform an operation at each stage. So we're going to take a dynamic programming algorithm approach to defining how to perform this transformation. Now, if you've never seen a dynamic programming algorithm before, or if you're like scared of them, as some people are because they are quite tricky, a dynamic programming approach typically is associated with creating a table of values where each entry in the table has some meaning. And the table could be two-dimensional most often, but it could be 3, it could be 4, it could be any number of dimensions, sometimes even 1. But the idea is that every item in that table is defined in terms of earlier items in the table. Or what does it mean to be earlier in 2 dimensions? But it's defined in terms of previously computed values in that table. So if you're a mathematician, or if you've ever studied discrete mathematics, this is a generalization of the concept of induction. You have your base case, which you know trivially, and you have your inductive case, in which every instance after the base case is defined in terms of instances prior to it. So whereas in mathematics it's used to make formal proofs, in computer science it's used to actually perform computations. I mean, you can use it to perform proofs if you like, but like it's more fun to do computations. Value statement on my part. So we're going to write out this table and kind of suspend disbelief for a little bit, and I'll explain to you what this table means. We're going to start off by having the star as the marker of the empty string. And we're going to write out our 2 inputs. So coding and coping. Now, these are going to be on the outside. Like, these aren't really part of our table. These are the labels. And the question is, what do we know trivially? Well, or rather, maybe we should ask ourselves. So, back it up. So the question now is, what do each of the cells in this table mean? So let's look at, let's say, this one right here. So what this is saying is, if I want to start with this string, so CO, how would I convert this string into COP? And obviously, again, our human intuition says, well, just perform an insertion, right? So you start here, you say skip, skip, and then stick in a P and you're done. But let's be more rigorous than that. So we're going to start off with CO, whoops, and we're going to start off with our cursor under the C. Now, here we're going to slide the cursor on because you see that the two letters are the same. We got CO. So now we're going to slide it along, and we've got our cursor here. And we say, okay, once again, the two letters agree, and we're going to say CO blank. And now we've got a blank. So what do we do here? Well, we perform an insertion. So we insert and slide it along. So COP, and now we're looking at an empty string. Now this string matches this string. Hooray, we're done. We've performed our transformation. And you'll notice that this one right here is the only step that counts as an edit. Everything else was just a match. So we say that the edit distance is 1. Now, you might look at that and you say, like, okay, cool, what's so hard about that? The problem is that there's actually a lot of paths you could take to find this transformation. Like, you could start with CO and then delete everything, right? So delete the C and then delete the O and then put in a C. Whoops, I should, there you go. And then put in an O and then put in a P. So we got 1, 2, 3, 4, 5 operations. And you're like, well, why would I do that? From a correctness perspective, that is an admissible transformation. What we want to ask ourselves is, how do we find the optimal transformation? And because, keep in mind, the optimal transformation, the number of operations that we performed as part of that optimal transformation is our Levenshtein distance. So we're going to define a number of operations here. We're going to define, remember I said that you can perform except, so when the strings match. You can perform replacements, you can perform insertions, and you can perform deletions. And what we're going to do is, if I want to say calculate the value that is going to enter into this cell, where each cell in this table contains the Levenshtein distance from, let's say, this one to this one, if I'm going to compute that optimal value, I'm going to do it in a dynamic programming fashion by starting with what we know trivially and then computing things out as we, according to our recursive definition. Let's not get into what that means just yet. So first off, what do we know trivially? Well, we know that if we start with an empty string, so let's say we start here with an empty string and you want to get to an empty string, you don't do anything, you win. If you start with a C and want to get to an empty string, you have to perform 1 deletion. If you start with a CO and you want to get to an empty string, you have to perform 2 deletions, and so on, 3, 4, 5, 6. And in a similar way with the insertions, if you start with if you start with an empty string and you want to get to C, you have to perform 1 insertion, and then CO, 2 insertions, etc. 4, 5, 6. Now the question gets interesting. How do we compute this value here? Or more generally, for that matter, how do we compute any other value? And the question we have to ask ourselves is, well, given the state of our table right now, what values are even computable? And what I like to define when I talk about dynamic programming algorithms, I like to define something called the dynamic programming frontier. And I'll show you what I mean by that in a minute, but effectively this square right here, this is the square that we can compute next because we know the values of all of its neighbors. And this is related to a concept called optimal substructure. And again, you may have read this in an algorithms textbook and be like, what are you talking about? You may have read it on Wikipedia and be like, what is this? I can tell you personally, it took me a lot of head scratching to properly understand this algorithm from just reading it on its Wikipedia page. But effectively what optimal substructure means is that for an item in this table, it can be defined using the previous, quote unquote, items in the table. So the frontier, in my definition, is the set of cells whose previous ancestors, whose previous cell values are all known. So in this case, the only efficient frontier, the only frontier value we have is this one. So what do we fill into that cell? Let's go back to our 4 operations. There are 4 things we can do. And I'm going to be abstract about this and give it to you in terms of indices, but I think hopefully we'll make it concrete in a minute. Hopefully you can kind of follow along. So let's go ahead and make a nice bigger grid here, right? All right, so we got 1, 2, 3, 4, 5, 6. And now I'm going to label these. We're going to call our string input S1 and S2. You know what? Let's say S and T, A and B. Let's use A and B. So A, this is going to be AI minus 1, AI. And keep in mind, we're going to be asking ourselves what goes in here. Call this CI. Now we're going to say B, J minus 1, B sub J. And the values we have here are C, I minus 1, J minus 1. Now C, I, J minus 1. Now we have C, I minus 1, J. And this one is going to be C, I, J. Now this is going to be an illustration that I'm going to use generally, because what you're going to find is that each of these operations corresponds. So the operations are accept, replace, insert, delete. Each of these operations corresponds to some transformation that I'm going to draw visually, and then we're going to define it geometrically or algebraically. So the first operation that we're going to define is acceptance or matching. Accept/match. And this is what we're going to do in, spoilers. This is what we're going to do here for this cell, because if you look at this, you see, well, they both have a C, so why would we first go here and then go there by first deleting, first by inserting and then deleting, isn't it? No, first deleting and then inserting, when we could just go straight here and accept. So acceptance is going to look a little bit like this. So I'm going to go ahead and paste in this. I'm going to go ahead and paste in this diagram. So the first thing we're going to do is we're going to copy the CI minus 1, CJ minus 1 value. So the first value the first potential operation we're going to say is Cij is equal to Ci minus 1, J minus 1 if one second. Let's do that again. So the first operation we're going to define looks like this. Cij, that's an ugly I. Cij is equal to Ci minus 1, J minus 1 if B, or let's be nice about it, right? AI is equal to B sub J. Now, this looks pretty straightforward, right? Like in this case, we have this. In this case, we have a C and a C. So we're just going to be like, all right, great. We're just going to take our cursor and move it over to the right. The second operation we're going to define is going to be replace. Go ahead and paste in our diagram one more time. This is when we, again, we're going to move diagonally, except we're going to say Cij is equal to Ci minus 1, J minus 1 plus 1, because we're replacing a string, so that counts as an edit, if A sub I is not equal to B sub J. Our third operation is going to be insertion. And one more time, paste our diagram in. What insertion is going to do is it's going to go from left to right. So Cij is equal to Cij minus 1 plus 1 if, or I don't think there's an if, I think it's just straight up a replacement actually. Yeah, so we're just going to take what is to the left of us and add it, plus 1. And number 4 is going to be, you guessed it, deletion. And deletion is going to take things down. So we're going to go from the cell above. So Cij is equal to Ci minus 1 j plus 1. Now, you look at all these operations, all these edits you can perform, and you realize, well, okay, this one, deletion counts as an edit, so it adds 1. Insertion adds 1. Replacement adds 1. Acceptance does not. So clearly you want to have as many accepts as possible over the course of your operation. And we'll see how this actually plays out. So to recap, we have acceptance, in which you go diagonally and you just copy the value of the number of edits. Because you don't have to make an edit, the two characters are identical. You have replacement, in which, again, you go diagonally, which is to say you swap the character and then move on. But you add 1 because you have to perform an edit. And then you have insertion, in which you take the value to the left of you and add 1. And then you have a deletion, which you take the value above you and add 1. Now, obviously, if these are multiple operations you can perform, these are 4 operations, but which one do you insert here? And the answer is you insert the result of the operation that gives you the smallest edit distance. So what I'm going to do now is I'm going to walk you through what computing the edit distance for this example looks like. So for the sake of argument, we could take this 1 and add to it and make it a 2. Or similarly, we could take this 1 and make it a 2. But why would we do that? Or I should also add, we can take this 0 and make it a 1. But then why would we do that if we have the option to take this 0 and copy it? Because the C's are both identical. And similarly, we're going to follow this logic for the rest of this column, right? So we're going to say COC, well, that's different, so that needs a deletion. This needs a deletion, this needs a deletion, this needs a deletion, this needs a deletion. Whoops, I can't count. That's a deletion. And again, going horizontally, 0, 1, 2, 3, 4, 5. Now, again, what happens to this cell? This cell, we have the opportunity to perform a movement in an acceptance. So we're going to go ahead and perform a copy, again, 0. And now notice how much more efficient we're getting. Well, we could do this and call it a 3. But why would we do that when we can just do this and call it a 1? So 1, 2, 3, 4. And similarly, 1, 2, 3, 4. Now we have ourselves our first case where we can't perform a simple accept. So we could do this. We could perform a deletion and get an answer of 2. We could perform an insertion and get an answer of 2. Or we could perform a replacement and get an answer of 1. So let's do the 1. And similarly, 2, 3, 4, 2, 3, 4. And I won't spoil it. I'm going to go ahead and, sorry, I actually will spoil it for you. And you can continue doing this. 1, 2, 3, 1, 2, 3. And then you say 1, 2, 2, and 1. And the value of this lower rightmost cell is the edit distance of this string being transformed into this string. And there's our solution. You now know that this string can be, that coding can be converted into coping using one edit. So let's get back to the interview. Hopefully, this gives you enough of a high level understanding of Levenshtein distance to understand how it works at a high level as as an algorithm. Interesting things start happening when we get into implementations, and that's what they're going to start talking about. And I'm going to illustrate what they're talking about in this diagram right here.
Kind of compare it that way. That's a pretty standard kind of dynamic programming type of exercise.
Yeah. And do you know the space and time complexity of that?
Oh shoot, let me think about it. I'm thinking space would be up to space is n, I believe, because you're keeping track of a parallel array essentially, unless it's n squared. If you have to keep track of like every pair of characters.
The standard approach, you build up a table that's n by n.
Yeah, I'm thinking about that n squared. Yeah, go ahead.
So it's n squared, but then there's this one optimization you can make that you never actually look more than one row behind as you're filling in the table. So there's this optimization that you can do it in O of n. But
I see. Yeah. Okay.
So let's illustrate that, right? So if you remember, and I'm actually gonna I can go back and forth here, right? If you look at the way in which I'm filling out this table, I'm first filling out the column and then I'm filling out the row, right? But coming back to my idea, my concept of the frontier, if I fill out this row, if I fill out this cell, I actually have a choice, right? These cells here both have they're both equally ready to be defined. They're both on the frontier, and I could do this one and then this one and then this one and then this one. That's a perfectly valid option, but what the interviewer is pointing out is that there's an optimization. If you do them column by column, you'll notice that 1, 2, 3, 4, 5. You'll notice that by the time it comes time to fill out this one right here, this O column, I actually don't need the first column. I could just take this and throw it out. And that's an optimization that allows you to take the space complexity of this problem from like n by m, which could be colossal. Like this is often used in some applications in which there's like thousands or even millions of characters in the strings. You can take that from this like horrible multiplicative space complexity down to a linear space complexity.
You can see how that optimization would work, yeah. That would be one way that I would do it. It would take me longer than 10 minutes to implement, unfortunately.
That's fine. So then, we're looking at O of n space, and then what's the time complexity of that approach? We're just like getting the full Levenshtein distance.
Yeah, time complexity I think is O of n because you you basically go through. You're basically filling out this table in each step of each cell of the table. Basically, you're only looking. You're not like looping through the entire like backlog, basically. So.
But how big is the table?
Table is n.
So it's got the table has all the characters on the first one as the rows, and then all the characters as the second one as the columns.
Right, correct. Is the smaller table you build, it's the size of the diagonal of that array, I believe. Is that correct, or?
So it's an n squared table. So you have all the characters on the top, and then the optimization is what you're saving, but you still have to fill in every.
Okay, got it.
Table.
Oh, okay, I see.
That's a good base. Is like O of n squared time and O of n memory.
Yeah.
But then the question is there a way to improve that? And obviously, in the worst case, like if the tolerance were the number of like letters, and you still had to fill in that whole table, then even like the worst case in any implementation is also going to be out that far. But sort of what we're trying to do here with the going incrementally through and shortcutting it is trying to see if we can find a way to stop it early, so that in the best case we're not filling in that entire table. We're making
you'd terminate early somewhere.
Right.
Okay.
So let's talk about how you can terminate early. Well, first off, if you have an example where this value, let's say like this, your tolerance is 1, but you have, let's say, I don't know, I'm gonna make this contrived here. You have some value here. You have like a wall of like 7s, right? Well, clearly, the stuff down here is going to be greater than or equal to 7. So that's you can terminate early there. So your threshold allows you to terminate early if it is impossible to have a value smaller than the threshold. The other thing worth pointing out, and I think they're going to get to this in a minute, is that consider this example. Suppose your threshold is 2. Every value greater than 2 is effectively infinity, which means let's go ahead and erase every value greater than 2. All these values that I've just gone ahead and erased, they never need to be computed because they may as well be infinite. Because the moment suppose you're filling out a column, right? Suppose like you're filling out this column here. The moment you go beyond 2, you just say infinity. Boom, done. Like, I can stop. Because the values from here, if you're going column by column, the values from here on down are going to be at least infinity. You will never decrease the edit distance over the column. So in practice, what ends up happening is that you have this like band, this you can imagine this like colossal matrix. The proper solution fills out this entire grid, but if you have a band, then you can do this thing where like you only really need to fill out the entries that are in here, because anything beyond that is either going to be way too small or way too big.
Okay, that's interesting. Yeah, I'll try to see if I can get that working after this. That would be cool.
Yeah. So another thing, just to throw it out there, ready to go, is if you take a look at this tolerance, you can think of so you need to get rid of the this piece here with the lengths, because you can't do anything with the lengths.
For sure, yeah.
But you can take a look at this step here, where you can think of the problem as being if the two characters that you're looking at are not the same, one of two things could be happening. It could be a deletion, in which case you sort of used up one of your tolerance, and then you're just repeating the same problem for the substrings afterwards.
Yes.
Or an insertion, and then you're doing the same thing. So you basically call.
I see.
So and with the iterators, I'm not sure. Not sure if you could make that work with the iterators instead of just using like indexes into the string. But it would basically be that you would call install compare twice on the two possible.
Yes.
Like, was it an insertion or was it deletion, with the tolerance like minus kind of thing.
Yeah, and you would basically return the OR of those two.
Right.
Okay.
Yeah. So just something to think about if you have time and want to work through that.
Yeah, cool. Thanks so much. That was a lot of fun.
All right. Well, take care, and good luck with all your interviewing.
Thanks. You as well.
All right.
All right. Have a good one. Bye-bye.
All right. Well, that is that video. I hope you found that interesting. Levenshtein distance and like dynamic programming as a family of algorithms are really fascinating. They're not the only class you need to know, but I hope you find this as an interesting introduction. I hope you also found the tactics that I described here and the thought process that I described helpful. In terms of what I would rate this candidate as, how I would evaluate them, I would make a higher recommendation. Granted, it's a little bit tough to do that with a short interview. Clearly, I would have liked to see an interview where they had the full hour. But under the circumstance, I would say that they can clearly code. I give them like, 70% on coding. And their reasoning about algorithms is solid. I don't think the interviewer gave them a chance to really shine. I think he gave him, he sort of led him on a little bit. But to be honest, the conversation was cogent. This was a mentoring session also, rather than like a full-on like formal in-character interview. So you can be a little bit soft here. I think this person would have done great if I imagine this person would have done great rather in their proper interviews. So yeah, I hope this was helpful. Hope you find this useful. If you have any questions, comments, concerns, leave them in the comments, and I will do my best to answer them if we do another video. Thank you very much, and good luck with your interviews.